This section covers the Policy Manager implementation of the 34K cores. The Policy Manager is a device that works with the dispatch scheduler of the core. The objective of the Policy Manager is to help you control the performance of each thread in your system so you can achieve your desired performance allocation of the CPU. This is commonly called Quality of Service, or QoS. The Policy Manager is a device external to the core, so you may change it to suit your needs. The core includes a choice of two types of policy managers: a basic round-robin policy manager that gives equal weight to all threads in the system, or a weighted round-robin policy manager where threads are placed in different priority groups. The rest of this section will cover the use of these two policy managers. Your design can change either of these policy managers, or you can create your own. The round-robin policy manager implements an equal scheduling algorithm. All threads have the same priority, and all threads have the same weight. The two thread scheduling registers, TC schedule and VPE schedule, have no effect for the round-robin policy manager, and reads from these registers will return a -1, or all bits set. For the weighted round-robin policy manager, a thread can belong to one of four groups, 0 through 3, with 3 being the highest group priority. Each thread in the highest group will run in round-robin fashion until there are no threads runnable within that group. Then, threads in the next group will run in the same fashion until a thread in the higher priority group becomes runnable. A thread is assigned to a group by the GPR field in its TC schedule CP0 register. The simple weighted round-robin policy manager described in the previous slide might cause a thread to be starved of any cycles. It could also cause a deadlock condition if a higher thread is dependent on an action of a lower priority thread, and the lower priority thread never gets to run because higher priority threads are always runnable. The weighted round-robin policy manager can be configured to rotate priorities, but still give the highest numbered groups more, but not all, of the CPU time. This guarantees all threads will run, but some will run more than others. Rotating priorities are controlled by the GPO bit in the VP schedule CP0 register. When this bit is set, static group priorities are used. When it is cleared, priorities are rotated between groups. The threads in the highest number group get a chance to run twice as much as the next lower priority group. Since each group can have more than one thread assigned to it, for a rotation where a group has the highest priority, all runnable threads within that group will get to run. Here is a table that illustrates the priority rotation. Each column is a rotation and shows the group priority for that rotation. The highest priority is circled. Let's look at column 1. The number in column 1 represents the priority the group has for that rotation. So here you can see the priorities match the group number. Therefore, group 3 has the highest priority and group 2 the next, and so forth. In column 2, the priorities have rotated, so now group 2 has the highest priority. To go through a full rotation cycle, it takes 15 rotations. Note, this is not processor cycles, as you will see on the next slide. After 15 rotations, you can see group 3 has the highest priority and could run twice as much as group 2, 8 times versus 4. Group 2 could run twice as much as group 1, 4 times versus 2, and group 1 could run twice that of group 0, 2 times versus 1. The chart shows the cycle effect of having more than one TC in a group. There are 4 threads in this system. 3 of the threads have been assigned to group 1, and 1 of the threads is assigned to group 0. The first column shows the cycle count. The second column shows us which rotation out of the 15 the policy manager is in. The remaining columns show the priority of each group for each cycle. Let's look at row 1. As we saw in the previous slide, the group number and the priority number match for this first rotation. Since there are no threads in group 3 or 2, the highest priority group is group 1. Because there are 3 threads in group 1, each one of those threads gets 1 cycle each, so the threads in group 1 use up the first 3 cycles. Since all threads that are runnable in group 1 have run, the priority rotates at cycle 4. This time, group 0 has the highest priority, so the one thread in that group runs for 1 cycle. Since there is only 1 thread in group 0, the priority will rotate again at cycle 5, where group 1 is again the highest priority group with runnable threads. Each thread in that group runs 1 cycle in turn. Then the priority rotates again, but for this rotation, group 1 is still the highest priority group with runnable threads, so it will run for 3 more cycles. This slide and the next continue to show the rotations and the running for each cycle. This slide shows the end of the rotation and totals the number of cycles each group used. Let me summarize what the previous slides demonstrated. What you see is each thread in group 1 ran twice as much as a thread in group 0. Since there were 3 threads in group 1 and 1 thread in group 0, then to complete the 15 iterations of a full rotation cycle took 35 cycles. Out of the 35 cycles, the 3 threads in group 1 had the higher priority to run for a total of 30 cycles. Each thread in the group getting an equal share. Each thread ran for 10 cycles. Out of the 35 cycles, the single thread in group 0 had the higher priority to run for 5 cycles. So you can see that each thread in group 1 ran for 10 cycles, and each thread in group 0 ran for 5 cycles, which accounts for any thread in group 1 running twice as much as a thread in group 0. I am going to show you an example of the weighted round-robin policy manager executing in the Eclipse debugger within our Navigator ICS product. This example has 4 TCs. 3 TCs are in priority group 1 and 1 is in group 0. So we expect to see the 3 threads in group 1 execute twice as much as the thread in group 0. So you can see I've set a breakpoint at the MIPS yield function in the count function. And I also added a couple of the group priority scheduling commands. You can see I'm going to set this thread to priority 0, and the rest of them are going to be set to priority 1. Now I'm going to debug. So I started the debug session and I'm at the first instruction of the main program. So now I'm going to continue and we'll see it run to the yield. Now I want to bring up a global variable the TC counter, and I'll expand that. If you look at the function, you can see that the counter is going to go to 2000 and terminate. Each thread will yield once it hits 2000. And we can see that everything but thread 0 has actually already hit the 2000 mark. And thread 0 was the one with the least priority. So each one of these threads ran twice as much as thread 0. If we continue this, we'll stop another couple of times while the other threads exit. And we can see that thread 0 continued after the other threads exited and reached its terminal count.